On the afternoon of the 14th of August, 2003, 14 transmission lines in the eastern United States were opened by distance relays measuring load. A distance relay has two inputs, the voltage at its terminal and the current through it. From those it computes an apparent impedance, and if that impedance falls inside the region somebody set it to protect, it opens the breaker. The relaying committee's working group states the relationship as one equation. Apparent impedance is voltage squared divided by apparent power, so the reading does not need a fault in it. Voltage falls, power rises, the apparent impedance collapses toward the origin. The larger the magnitude of the apparent power, the smaller the radius. A worked case. A North American Protection Task Force in 2006 set a Zone 3 element at 150 ohms against a load, presenting 57 ohms at 0.85 per unit voltage. 57 ohms is not near the setting. It is 93 ohms inside it, and nothing in that picture is broken. An American standard for distance relay application states the hazard. There may be insufficient margin to ensure that the apparent impedance due to heavy load does not enter the operating characteristic of the distance relay. That is what 14 lines did that afternoon. About one of them, the joint investigation wrote a single sentence. The relay operated as it was designed to do. 14 lines, and they were not one kind. In April 2004, a joint American and Canadian investigation wrote down what the commonest protective device on a transmission line can see: the current through it and the voltage at one end. Its own words. The most common protective device for transmission lines is the impedance relay, also known as a distance relay. It detects changes in currents and voltages to determine the apparent impedance of the line. Then the sentence that shapes everything after it. Each relay is actually 3 relays within one, with each element looking at a particular zone. Zone 1 reaches 80% of the line, with no time delay at all. Zone 2 reaches the whole line and a little beyond, and waits 15 to 30 cycles. Zone 3 looks for faults well beyond the length of the line, and should not trip the breakers under typical emergency conditions. The working group gives its delay as typically 1 to 2 seconds. Every one of those numbers is a choice. 80% of a line, 15 to 30 cycles, 1 to 2 seconds. A person set each, and none is a measurement. None is on the scale a control room works at either. An operator's minute is 60 of these rulers end to end. Stretch the same ruler until it holds 2 seconds and Zone 3 finally lands inside it. The fastest element is then half a graduation wide. Zone 1 does not wait at all. Several of the elements that opened lines in Michigan that afternoon were Zone 2s, set to reach more than 200% beyond the line they protected, with no intentional time delay at all. That is the investigation's own description. A Zone 2 set to behave like a Zone 3, reaching past the far end of its line by a factor of 2, acting immediately. On a delay axis, the place a Zone 3 element belongs is out at 1 to 2 seconds. Its delay is the entire reason it may reach that far. The elements the report describes were at 0. 2 other lines that opened that afternoon were not Zone 3. The Homer City to Watercure and Homer City to Stoll Road lines do not have Zone 3 relays. That passage is about a separate event, and the report never counts them into the 14, which leaves the 14. The investigation gives a count, and one subcount, several in Michigan. It does not say what the others were, how far they reached, or how long they waited. The federal regulator confirms the count and adds nothing to it. And the count is not a fraction. These are the lines identified at the start of the cascade, not 14 out of everything that opened. Most of this population cannot be placed on the axis at all, and the film will not invent positions. The rest are a count and nothing more. A line called Dale to West Canton carried between 160, and 180% of its rated load for 20 minutes before anything opened it. 20 minutes at nearly twice the load the line was rated for, with protective relays watching the whole time. The investigation put that measured interval into a counterfactual of its own. If these lines had not tripped quickly on zone 2s and 3s, it wrote, each might have remained heavily loaded for as long as 20 to 30 minutes before the line sagged into something. Might have remained. That is the report's verb, and it is this film's. Set that against the delay the elements were carrying. A zone 3 waits 1 to 2 seconds. 20 to 30 minutes is 600 to 1800 times longer for the same decision. Nothing in that account is a broken device. Each element saw an apparent impedance inside its characteristic and acted quickly, which is what a fast element is for. The relays were the fastest correct thing on the network that afternoon. But the 20 to 30 minutes is time that then did not exist. Reading page 82 that way is this film's reading of the passage. The report does not print the sentence. So the largest interval in this chapter is one that never happened, and it is longer than everything that did. They removed the time somebody might have used. In 2006, a North American Protection Task Force wrote down where the loadability criterion's two numbers came from: 0.85 per unit voltage and a 30-degree power factor angle. Both were readings taken while the system was under stress. Its words: the 0.85 per unit voltage was an observed value when the system was in an extreme condition. The 30-degree power factor angle was also an observed value while the system was under stress. 30 degrees is not an extreme value. Some power lines operate at 45 degrees. The same document dates it. During the August 14th disturbance, a 30 degrees power factor angle was observed prior to the unstable power swing between Michigan and Ontario. 6 years later, the federal regulator read a second number off the investigation's own figure. The power factor angle recorded at the time the line tripped was about 27 degrees. 27 inside 30. Purely from the power factor angle viewpoint, the regulator writes, the trip may still have occurred even if the requirement of 30 degrees was met. It quotes the task force against its own standard. The loadability recommendations are not absolute system conditions. The voltage may be below 0.85 per unit and the power factor angle greater than 30 degrees, and on whether the standard would have changed that night. We do not think that it is possible to definitively reach these conclusions on the present record. The whole margin was 3 degrees. In March 2010, the Federal Energy Regulatory Commission was asked to set a maximum reach for these elements, and wrote that it would not. Its words, with two acronyms, opened out. We decline to adopt the proposal and will not direct the Reliability Organization to develop a maximum Zone 3, Zone 2 reach. The standard that governs instead is called PRC023, and it never names the element. What it bounds is loadability. It sets two evaluation conditions: 0.85 per unit voltage and a 30-degree power factor angle, then 13 criteria, of which a setting must satisfy anyone. 13. Not one rule with exceptions. 13 alternative ways to be compliant, and this film's research carries the wording of one. That one is the best known. Do not operate at or below 150% of the highest seasonal facility rating for the available defined loading duration nearest 4 hours. Read that wording carefully. It is not the recommendations. In February 2004, the Reliability Board recommended 150% of the emergency ampere rating. Emergency ampere rating out. Highest seasonal facility rating in. 2 documents 6 years apart, and the substitution changes what the number is a percentage of. The other 12 are not in the material this film was built from, so 12 of the gates on screen carry no label. It bounds loadability. It never bounded reach. 10,914 relay terminals at 200 kilovolts and above were examined, and then 12,273 more. That is the post-blackout review program as the federal regulator records it. Over 3 years, 150,000 hours of labor, almost $18 million, and 65 million of equipment changeouts. What all that work did was change settings. It did not remove the element. 20 years later, in September 2024, the North American Reliability Organization published this. The most common type of remote backup protection for phase faults on transmission lines is phase distance relaying with fixed time delay. The same document on whether the tension is resolved. In many cases, it may not be possible to set the remote backup within the loadability requirements of the standard without some form of load encroachment. Practice is split, and both halves are in print. The Relaying Working Group. Some utilities have taken their remote backup Zone 3 relays out of operation altogether. The 2004 report. Many regions in the United States and Canada have eliminated the use of Zone 3 relays on 230 kilovolt and greater lines. Which of those describes most of the fleet is a question this film cannot answer. No census of Zone 3 relays in service was found in any source reached. Not a count, not a range, not an estimate. The reviews counted the terminals. Nobody counted the zones. In 2011, the first year of mandatory reporting, 28% of protection misoperations in North America came from an incorrect setting, a logic error, or a design error. 20% came from a relay that failed. Across the following decade, the first ran at about 30 to 32%, the second at about 18 to 19. In the most recent window, 2021 to 25, settings, logic, and design run at 31 to 34%, and relay failures at 15 to 18. The two series do not converge. The hardware figure is falling, and the engineering figure is not. The instrument needs one repair first. From the 2022 edition, the cause code was split into 3, so the series appears to drop 8 points in a year in which nothing changed. The comparable figure is the sum. The most recent year reads like this: 1,087 misoperations in 2025, incorrect settings 22%, logic errors 5, design errors 4, against relay failures at 15. That is the 2026 edition, and the edition matters. The same organization prints the 2021 count 3 different ways. An earlier task force went a level down into 306 settings misoperations. Element setting error, 48%. Improper coordination timing, 22. Overreaching zone 1 and instantaneous elements, 17. They do not add to 100, and the source does not say what is missing. The device is rarely the thing that failed. A distribution circuit that has tripped will try to close itself again somewhere between 1 second and 180 seconds later. That interval is the dead time, and the range is the British Engineering Recommendation's own. Auto-reclose dead times typically between 1 second and 180 seconds. Put a generator on the far side of that circuit. When it opens, the machine and its load are cut off from the system, and for a moment neither knows it. The recommendation gives 2 reasons. The protection exists to prevent the generating plant supporting an islanded section of the distribution system when it would or could pose a hazard. Then the second, about the machine itself. If the plant continues to operate, there is a risk that when the network supply is restored, the generating plant will be out of synchronism with the total system and suffer damage. Out of synchronism describes what happens while nobody is watching. The orphaned machine is no longer held to the frequency of the system it was part of. It drifts, and the dead time runs. 1 second, 3, 30, 180. Nothing in that interval is a measurement of the generator. It is a setting on the circuit chosen for the circuit. No document reached for this film gives how fast the drift is, or where it gets to, so nothing here is drawn to a scale. Then the breaker closes. It closes on whatever angle is there. On the 22nd of May, 2016, a fault on a single transmission circuit in Great Britain took more than 400 megawatts of distributed generation off the system. None of that generation was islanded. The fault was on the transmission network, away from all of it, and it was cleared. What disconnected them was a loss of mains technique called vector shift. It watches the voltage phase angle from cycle to cycle, and when the angle jumps, it concludes the plant has been cut off. A remote fault produces that jump. So does an ordinary change in the network. Sudden changes to the impedance of the distribution network can have a similar but smaller effect. This is not a loss of mains event, but is known to cause maloperation of loss of mains relays unless properly accounted for. 3 situations outside the device. 1 reading inside it. The same verdict every time, correct in the only world the device can see. The third is the one it exists for, and that is where the studies land. Vector shift relays are, in general, ineffective at detecting the existence of an island. Therefore, they do not perform their function as expected. University work, quoted in the regulator's decision. What the reading looks like in that case is not in this film's research, so it is not drawn. The regulator prohibited it for new plant in December 2017, and the recommendation now carries the clause outright. Vector shift is not an acceptable loss of mains protection. Approximately 2 gigawatts of small generators in Great Britain sat behind relays that disconnect them if the rate of change of frequency goes above 0.125 Hz per second. The operator's own appendices state the consequence as an obligation on itself. As a result, the operator must keep the rate of change of frequency at less than 0.125 Hz per second to prevent loss of this generation. That is an inversion. A relay setting on embedded plant became a constraint on a country's whole transmission system. This film's research carries 4 annual figures alongside that constraint and does not record the line item the operator files them under. 30.3 million pounds, 30.7, 59.2, and 143.6 million in 2018 to 19. The same material carries a projection of at least 600 million pounds across 2018 to 24. A projection is a chosen number, and it is drawn as one. The alternative is priced in the same appendices. To increase the inertia of the system to allow 1 megawatt more of in-feed loss generally requires adding 20 megawatts of synchronous generation, approximately 10 times more expensive. So the constraint holds because relaxing it runs at 20 to 1. And the thing being held is not a rule. It is a population of devices, each with a number chosen by somebody. 20 megawatts bought 1 megawatt of headroom. On the 23rd of July, 2014, the British regulator published a decision whose second page states the cost of the change it was approving. The change was to make loss of mains protection less sensitive, so that it would stop disconnecting generation during ordinary events on the system. The paragraph in full, desensitizing the rate of change of frequency loss of mains protection setting increases the risk that, when an island network forms, generation connected to it does not disconnect and the island remains energized. This increases the risk to people near the island network and increases the risks of out-of-phase reclosure. Before approving it, the regulator consulted the Health and Safety Executive under Section 3C of the Electricity Act. The executive then wrote to all 20 network licensees. The residual risk of accidental electrocution was quantified, 6.28 times 10 to the minus 7. It is a computed figure in a public document with a date on it and a body's name at the top. The change was approved. The framework calls that broadly acceptable. On the 1st of August 2014, the new setting took effect for plan of 5 megawatts and above, 1 hertz per second for non-synchronous plant, 677 sites, 677 out of 50,012, 1,445 between 1 and 5 megawatts, and 47,890 below 1. The second and third decisions in force from February and July 2018 covered new plant, not the population already on the network. The fourth, in force from the 1st of September 2019, was retrospective, all existing plant complying by the 31st of August 2022, 5 years from the first decision to the one that reached the other 47,000. The work group wrote down its own problem. Most of them have little or zero interaction with network licensees or regulators. The scope does not close either. A second primary document implies about 9,600 sites in scope, not 50,000. Both are primary, neither is reconciled. One requirement was there from the first decision. The rate must be measured to be continuously in excess of the required setting for 500 milliseconds before activating the trip relay, and the recommendation forbids the obvious way to build it. Setting the number of cycles on the relay used to calculate the rate is not an acceptable implementation of the time delay. The number of cycles is not the delay. At 4:52 and 33.490 in the afternoon, on the 9th of August 2019, lightning struck a 400 kilovolt line between Eaton Socken and Wymondley. 4 days earlier, the regulator had published the retrospective decision. Start at the scale a control room works at. 1 minute. Inside it, the frequency of the British system falls, is arrested at 49.1 hertz and falls again. At 4:53 and 49.4 seconds, at 48.8 hertz, low-frequency demand disconnection operates. 931 megawatts. 1,152,878 customers. Go down 1 decade to 10 seconds, and that single event separates into 4. Down another to 1 second, and they separate properly. About 150 megawatts of embedded generation on vector shift. Hornsea, from 799 megawatts to 62. Little Barford steam turbine, 244 megawatts, and about 350 megawatts of embedded generation on rate of change of frequency, the figure the reports print. All 4 are inside 1 second, and the first 2 are inside the first half of it. 1 more decade down is the ruler from earlier in this film. 50 cycles, same pitch. That is the scale the devices were working in. The control room's minute, and that ruler are 4 orders of magnitude apart. The devices had the first second. The network operators reported 462 megawatts of embedded generation lost, and could not say which protection took it. The system operators' report says why. They were unable to determine whether a specific generator tripped due to rate of change of frequency or vector shift. So the split was constructed. The vector shift loss was simulated at about 150 megawatts and taken off the total. The remainder was assigned to rate of change of frequency. 3 official documents print the result. One prints 350 megawatts. The other 2 print 350 to 430. Underneath all 3 there is one reported figure, one simulation, and a subtraction. The regulator's footnote says why. Distribution network operators do not monitor output from distributed generators in real time. And it states the consequence plainly. There is a significant possibility that this volume is in excess of the transmission-connected generation lost during the event. The same blindness runs through the demand figures. The operator records 931 megawatts disconnected. The net demand reduction seen by the transmission system was only 350 megawatts, indicating that approximately 550 megawatts of additional distributed generation was lost at this point. The program that changed those settings never published an account of itself. What exists is one committee minute from April 2024. 5 sites still non-compliant at Northern Power Grid, 31 at SSE. 2 operators, not the program and not the 50,000 sites. The same minute says that team is thought to have disbanded.